So now we're going to focus on the right side of the equation a little bit just to understand this work and change in energy. So we focus a lot on how we calculate work. Now we're going to talk about what the change in energy looks like. And so like work, energy is a scalar quantity. So don't think of it as a vector. It does not have a direction. It can be positive or negative, just like we talked about work can be positive or negative, but you can have negative scalar values, right? So we've spent so much time on vectors and teaching that, positive and negative is direction, but you can have negative things. You can have negative temperature. That's a scalar, not a vector. You can have so there are examples of where you can have positive and negative scalars like you do normally in your other math classes before. So just keep that in mind that it's not the direction anymore because these are not vectors. Now, remember when we derived this, we derived this expression from our F net equals ma. It was this 1/2 mv squared minus 1/2 mv0 squared. And so we want to talk about this quantity here as the change in energy. And this thing is called the kinetic energy. This 1/2 mv squared term is the kinetic energy. And so this difference is the change in the kinetic energy. So what do we mean by kinetic energy? It is the energy of an object by itself. It's the most basic form of energy we start with. Anytime you include an object, if it has any motion at all, it's had any speed, it has kinetic energy. Kinetic energy is related to its mass and velocity. The more speed it has, the more kinetic energy it has, or the more mass it has. So think of it as like a giant bowling ball. It's rolling down, and it's going to knock over a bunch of pins, right? The heavier the ball, or the faster you throw that ball, the more kinetic energy, the harder it's going to hit those pins. Right? And so that's a huge part of what affects the kinetic energy of that ball is how fast you throw it and how heavy the ball is, right? And if it's not moving, it has zero kinetic energy. So that's pretty much it. So let's understand how this process generally works. So we're going to focus on not just the energy, but the change in the energy. That means there's always 2 points. We're always talking about the kinetic energy, not at just a single moment, or at least when we're using work equals a change in energy, we're talking about the energy at 2 different points in time. The start, or we call the initial, and the end, or the final. Just like we did in kinematics, there's an initial, there's a final location, and we're talking about the kinetic energy at those 2 points. So when we look at our overall energy process, this is our problem-solving process when it comes to work and energy. We're going to draw a free body diagram. Why? Because we need to determine this part. This first part is to determine whether there's any work, what the work side of the equation looks like. Actually, the first 4 steps are literally just to figure out what work is happening on the system. Then the second part is the energy part, the change in energy portion. It's just basically calculate what's the energy at the start of the motion. And start is kind of in quotes here, right? It's just wherever you designate as the initial and where is the end of the motion. The 2 points in time we want to analyze. Okay, so we're going to draw the free body diagram, define the system, which we're going to focus a lot more later on. For each force, determine if it does any work and set up an expression or calculate the work. Sometimes we might not be able to calculate it because it's something we're going to use to solve, so either an expression or directly calculate it. Then we're going to calculate the kinetic energy at the start of the motion, the kinetic energy at the end of the motion, and then apply this equation here. So let's see how that works in here. So we have a box of 3 kilograms pushed horizontally with a net force of 10 newtons. So 10 newtons this way. After the block has been moved 10 meters, let's say it's not a net, it's just a constant force of 10 newtons. After the block has moved 10 meters, how fast is the block moving? Assume the block starts from rest. Okay, so then the block later on is moving with some velocity v, and we'll just say it's a frictionless surface. Okay, let's keep it simple here, because otherwise I'd have to specify that. So let's draw a free body diagram, right? We're going to have mg, we're going to have normal force, and we have this 10 Newton force to the right. Okay, and that's our first step. Let me get the pictures of those steps here. All right, so we've drawn the free body diagram here. We've done that. Now we define the system. This case is just the box, so the box. Later on, we'll talk about if we include more objects, more complicated scenarios. For each force, determine if it does any work. Well, the displacement is to the right here, right? This is the displacement, and that's, 10 meters? So the normal force doesn't do any work because it's perpendicular. Same with gravity, because the displacement vector is only pointing to the right. Only the 10 Newton force is going to do work. So our work calculation is going to be, because they're both pointing to the right, all right? They're both positive quantities. It is 10 times 10. and they're parallel, so that's going to be 100 joules of work. Let's calculate the kinetic energy at the start. At the start, it's I should say it's from rest. Blocka's starts from rest. Clearly, I didn't put enough information in this question, so the velocity here is 0. So the initial energy is 1/2 mv squared, but because the initial velocity is 0, the initial speed is 0, has no kinetic energy. The final kinetic energy, so there's that. Final kinetic energy is 1/2 mv squared, which is 1/2 3, and then v squared. We don't know what v is. And then we're going to do work as the change in energy. So 100 is going to equal to this. This is 3/2 v squared. 3/2 v squared minus 0, and you can then solve for v at that point. We would multiply by 2/3, and then take the square root of that. And that would give you 8.16 meters per second, like that. Now, we could have done this with forces and kinematics. You might ask, Alan, this seems like kind of a lot of work. Why don't we just do it with forces and kinematics? And you would have gotten the same answer. Okay, let me just point that out to you. So let's say the displacement, if we think about the motion, we'll say right is the positive direction. 10 meters to the right, initial velocity is 0, final velocity we don't know. We would like to know. The acceleration we don't know, nor do we know the time. However, we can use F net equals ma to know the acceleration in the x direction. In the x direction, the 10 newtons to the right, that's equal to 3 times the acceleration. The acceleration is 10/3. And then we can use a kinematic equation that relates these 4 variables, right? And so you got v would be the square root of v0 squared. That's 0 squared plus 2 times 10/3 times 10. And if you do that, you get the same answer. Right, yeah, you'll get the same answer here, and I'll get 8.16 meters per second, right? So I get the same answer, but there's an aspect that we're trying to hear conceptually, is I'm doing work and I'm giving the object kinetic energy. That's the conceptual thing. Yes, from a mathematical point of view, forces and kinematics, you can think of it as I'm applying a force, I'm giving it acceleration. Kinematics then tells me how fast it will be moving at that point. Both are 2 different ways to describe the same thing that's happening, right? But the work and energy is going to be more useful as the scenarios get more complicated, in which case forces and kinematics would require you to know way, way, way more advanced math. Not even just AP calculus, but you would need to know multivariable calculus to understand vector directions and rotation, and how things move. It would get very, very complicated very quickly. So this is why work and energy is such a powerful tool, is because it allows us to not deal with the vectors notation stuff, and it allows us to ignore certain things that aren't relevant to overall the problem. So let's go through another example. So I have a ball of 2 kilograms dropped from a height of 10 meters. Right, so this is 10 meters. Calculate the speed of the ball before it strikes the ground. So it's going to fall here using the work energy theorem. Okay, so let's start with our first step. We're going to draw our free body diagram. Or actually, let me get the steps back up in here. So let's draw our free body diagram. Okay, well, he's going to fall. He's going to have mg here, only one force. Define the system. Again, the system for now is just going to be the ball. For each force, determine if it does any external work. Well, gravity is external to the ball, or it's caused by the Earth, which is external to the ball, so it does do work. The displacement here is downwards, by the way. Okay, and so it's 10 meters pointing downward, right? Because that's from where the start to end is. And so then we say, like, oh, it does positive work, right? It's going to be mg times 10. Let's just call it h. We'll call it h. mg times h. Okay, so it's positive because they're both pointing in the same direction. How about the initial kinetic energy? It's going to be 0 because initially it's not moving. The final kinetic energy is going to be 1/2 mv squared at the end here. And so then we apply, right, it's just going to be moving with some speed here. If we apply work as the change in energy, work is going to be the final energy minus the initial energy. That's going to be mgh is equal to 1/2 mv squared minus 0. M's cancel, and you can solve for v. V would be square root of 2gh, like that. And then you could plug in 10 and 10 if you wanted to, and plug in the masses. Note the mass didn't matter, and if we did kinematics, we would get the exact same thing. Okay, if we make down the positive direction, the displacement would be h, the initial velocity would be 0, final velocity we're looking for, and the acceleration would be g. right? And then the kinematic equation here, we would use this one. So we get V is going to be the square root of V naught squared, which is 0 squared, plus 2GH, which is square root of 2GH. So we get the exact same answer. And again, we pick simple scenarios just so you understand the process. But we will do more complex problems as we proceed, as we get more complicated. But there are certain things that are really beneficial to understand using work and energy, where the math is either extremely complicated or even impossible with the level of math that you guys know at this point.